Chapter 16, Quantum Rotation. Section 16.3, Three-dimensional quantum rotors. The three-dimensional one-particle rigid rotor has a constant radius denoted by R0. The time-independent Schrödinger equation for this one-particle system is this: kinetic energy operator applied to psi, potential energy operator applied to psi. The sum is equal to E psi. The left-hand side is also H psi, where H is the Hamiltonian. X squared plus Y squared plus Z squared is equal to R squared. V is 0 when R is equal to R0. V is infinity when R is different from R0. That ensures the particle stays on the sphere. So this problem sometimes is also called quantum particle on a sphere. Now let's look at the conversion between the x, y, z Cartesian coordinates and the spherical polar coordinates. Let's look at this position. We have x, y, and z, of course, but also we can use r, theta, and phi to specify the same position. R is the distance between this position and the center. Theta is the angle between the r vector that specifies the position and the z-axis. And also we can project this vector r to the xy plane. And now we have this dashed line on the xy plane. The angle between this dashed line and the x-axis is phi. Now we have x is r0 sine theta cosine phi, y is r0 sine theta sine phi, z is r0 cosine phi. This is just trigonometric functions, and if this r is r0, we can do a projection of this vector to the z-axis. Therefore, the z component is just r0 times cosine theta. And now this dashed line, the projection of vector r on the xy plane is r0 sine theta. So this is r0 sine theta. Its projection on the x-axis is r0 sine theta times cosine phi. Its projection on the y-axis is r0 sine theta times sine phi. Again, x squared plus y squared plus z squared is equal to r squared. For this rigid rotor, r is just r0, and then we have this equation. We can also look at tangent theta. Tangent theta is this dashed line divide. Tangent theta, yeah, it's this dashed line over the z component, here. And we have tangent phi. Tangent phi is pretty simple. It's just y over x. So we just do y over x. We have sine phi over cosine phi. That's tangent phi. The range for theta in quantum chemistry is defined to be from 0 all the way to pi. Alright, so when the vector is pointing up, theta is 0. When the vector is pointing down, theta is pi. We can also look at phi. Well, phi can be from 0 to 2 pi. So if this projection is on the x-axis, that's just 0. So we can rotate 90 degrees to the y-axis, 180 degrees to negative x, 270 degrees to negative y. And finally, after we rotate 360 degrees or 2 pi, we get back to this position. Again, in quantum chemistry, we use r, theta, and phi to specify the position. Theta corresponds to the latitude of Earth. Phi corresponds to the longitude of Earth. However, we have a slightly different lower limit and upper limit comparing quantum chemistry and geography. In geography, latitude is from north 90 degrees to south 90 degrees. the longitude is from west 180 to east 180. Over here, theta is 0 to pi, phi is 0 to 2 pi. However, they do share something in common. It's just between North Pole and South Pole, the latitude spans 180 degrees or pi. Over here, it's also 180 degrees or pi. The longitude, well, the longitude spans 360 degrees or 2 pi. Same here. Phi spans a range of 2 pi or 360 degrees. Alright, we'll just imagine there's a axis pointing from the South Pole to the North Pole. That's the z-axis. Alright, that's the z-axis. We can now derive the Schrodinger equation in spherical polar coordinates. When r is r0, it's easier. If r is not a constant, it's more difficult. Now let's do the derivation, assuming r is r0. So this is the Schrodinger equation. You can see I dropped the potential energy term because for this problem, three-dimensional particle on a sphere, v is just 0 when the particle is on the sphere. V is infinity when the particle is not on the sphere. So since v is just 0 when the particle is on the sphere, we just drop the potential energy term. We're going to use the chain rule. How does psi depend on x? Well, we can express this in terms of r, theta, and phi. So we look at how psi depends on r and how r depends on x. How psi depends on theta and then how theta depends on x. How psi depends on phi and how phi depends on x. But since r is r0, it's a constant. So really psi only depends on theta and phi. The first term is just 0. So how does psi depend on x? Again, we can use theta and phi as the intermediate variables. It's just the chain rule. Similarly, we can write out delta psi over delta y. It's just how psi depends on theta, theta depends on y, how psi depends on phi, and how phi depends on y. What about z? Fortunately, when we are talking about z, there's no phi, because if you look at this, delta psi over delta z is simply delta theta over delta z times delta psi over delta theta. We do not worry about this phi term because if you can just look at this, if I change the value of phi, how does the value of z change? Well, there's no change. Z simply does not depend on this phi, this longitude. So we can express delta psi over delta x, delta psi over delta y, delta psi over delta z in terms of theta and phi. The reason we don't have to worry about r is a constant. Now let's derive this one, delta psi over delta z. It's easier because z is a function of only theta, so we have this equation. Delta psi over delta z is delta theta over delta z times delta psi over delta theta. Over here, theta is the intermediate variable, and this is one of the applications of the chain rule. Now we're going to do derivation. We will insert another intermediate variable here, tangent theta. So this part, delta theta over delta z is delta tangent theta over delta z times d theta over d tangent theta. D theta over d tangent theta is the reciprocal of d tangent theta over d theta. So we have this. This part can be easily evaluated if you're familiar with single variable calculus. This part, tangent theta is the square root of x squared plus y squared over z, because the top is r0 sine theta, the bottom is r0 cosine theta. Finally, we have just this term, and then we're gonna just do a bit derivation. This part is just cosine theta squared. This part, we're gonna just hold the square root of x squared plus y squared constant, because x and y are held constant, so it's here. We just need to get the first derivative of 1 over z. It's negative 1 over z squared, and we have all this. And now we need to convert x, y to r theta phi, z to r theta phi, and then on top we have r naught sine theta. On the bottom we have z squared, therefore it's r naught squared cosine theta squared. We clean up everything, we get negative sine theta over r naught, delta psi over delta theta. We just converted this derivative to the polar spherical coordinates right here. The simplified notation is this: delta over delta z is equivalent to negative sine theta over r naught, delta over delta theta. We're not done yet, because if you look at the kinetic energy operator, it involves the second derivatives. Alright, now the second derivative with respect to z is simply, well, the first derivative operators applied twice. So you have delta over delta z applied to delta over delta z. And then we have this delta over delta z here and here. And we first clean up a little. We take this negative over 1 naught out. We have this expression. And then we apply delta over delta theta operator to everything inside the parentheses. We need to use the product rule, so we get this sine theta, its derivative is this, and then we copy this here, we copy sine theta here, we apply delta over delta theta to delta over delta theta. That's the second derivative. So we have this expression, and I can take the sine theta into the parentheses, and we got this. Well, in principle, we can also convert the second derivatives of psi with respect to x and y into polar spherical coordinates as well, using the same strategy. It's a lot more tedious because we have to worry about two variables, both theta and phi, when we are deriving this. If you are interested in this conversion, you can take a look at Appendix P. In Appendix P, I converted the XYZ coordinates to the polar spherical coordinates r, theta, and phi for the kinetic energy operator, or you can say the Laplacian operator. In the polar spherical coordinates, after we finish all those conversions from XYZ to r theta phi, we'll get this shorting equation in r theta and phi. It looks more complicated. The reason we do this is because, well, if you use XYZ coordinates, it's actually more difficult to solve that shorting equation. Mathematically, it's easier to solve the shorting equation for the three-dimensional rigid rotor using polar spherical coordinates. Especially since r is constant, we have only theta and phi as the only two variables in this equation. And over here you see it's negative h bar squared over 2i. I is the moment of inertia. I is mr squared. Since it's a rigid rotor, r is r naught. R naught denotes a constant radius. If you have a two-particle system, I is mu r naught squared. We need to replace the mass with the reduced mass mu. Still remember the definition of mu? 1 over mu equals 1 over m1 plus 1 over m2. Theoretically, we can solve this equation. The solutions are fairly complicated. The solving process is extremely tedious. So I'm just providing you the first few solutions here. 1, 2, 3, 4, 5, 6. Actually more than 6, because over here there are two solutions. Let's look at the first solution here. It's just a constant, but why it's 1 over the square root of 4 pi? Well, it's just because we want to have a normalized solution. So this is actually normalized. So if you integrate this with respect to sine theta, d theta, d phi, you're going to get 1. Alright, what do these two numbers mean? We have a number in the subscript. That's quantum number L. And we have another number in the superscript. That's M sub L. So we have this kind of format over here. And Y is the solution to the Schrodinger equation. Alright, so we have a bunch of solutions. This is the first one. The second one here, L equals 1, M sub L is 0, and you can see it's a constant times cosine theta. The constant is just the normalization factor. Cosine theta, remember, is proportional to Z, because Z is R0 times cosine theta. We have a couple complex functions here. It's a constant times sine theta times e to the power of plus minus I phi. These two are the solutions to the Schrodinger equation over here. But also remember, if we take the linear combinations of e to the power of plus minus I phi, we can get cosine phi, we can get sine phi. Cosine phi times sine theta is simply x over R0. Sine phi times sine theta over R0 is y. So this two combinations are proportional to x and y. And now over here we have more solutions. This one is proportional to 3z squared minus R0 squared. And the linear combination of these two wave functions are proportional to xz and yz. Also, we can just do a linear combination of these two complex functions. We can make cosine 2 phi, we can make sine 2 phi. Cosine 2 phi is cosine phi squared minus sine phi squared. Sine 2 phi is 2 times sine phi cosine phi. That's just mathematics. And you can see the linear combinations of these two functions are proportional to xy and to x squared minus y squared. Eventually you'll see this y is proportional to the wave function of the s orbital. This is proportional to the 2pz orbital, 2px, 2py orbitals. And now we have 3d z squared orbital, 3d xz, 3d yz. Over here it's proportional to 3d xy and 3d x squared minus y squared in the hydrogen atom. The reason I mentioned the hydrogen atom is because we can only solve the Schrodinger equation for the hydrogen atom exactly, not for any other atoms. Again, we can look at the linear combinations of some of the solutions. They resemble the SPD orbital. The first one is y 0 0, L is 0, M sub L is 0. Well, that's just s orbital. Remember, if you have s orbital, L has to be 0, M sub L has to be 0. It's a constant. That means it does not depend on theta or phi, and that means it has to be spherical. Only a spherical shape does not depend on theta or phi. Over here, y 1 0, L is 1, M sub L is 0. Isn't that a pz orbital? Also, we can see this cosine theta is proportional to z. Now we have two exponential functions over here, e to the power of plus minus I phi. The linear combination of this may result in cosine phi or sine phi, depending on whether you're doing addition or subtraction. Alright, so cosine phi is the sum of these two exponential functions over 2. the sine phi is the difference between these two divided by 2I. So anyway, we can get cosine phi and sine phi from the linear combinations of these two complex functions. Cosine phi times sine theta is x over r naught. Sine phi times sine theta is y over r naught. And they correspond to the px, py orbitals. And remember, in general chemistry, we have m sub l equals 1. Then when we have l equals 1, the m sub l can be plus minus 1 or 0 here. And therefore, we have 3 p orbitals. Over here, it's just mathematical proof. We can just express x over r naught and y over r naught as linear combinations of these two complex functions. We can sum up these two complex functions. I sine phi cancel. Alright, and then we get 2 times sine theta times cosine phi. It's proportional to x. We can take the difference between these two. Alright, so the difference over here, we expand them. It's just Euler's formula or Euler's equation. Cosine phi cancel. And then we get 2I sine phi in the parentheses. And the result is proportional to y. Well, we can also look at more complex d functions where L is 2. When L is 2, m sub L can be -2, -1, 0, 1, and 2. When m sub L is just 0, the solution is this. Well, it's actually just proportional to 3z squared minus r naught squared. Alright, so this part is equal to this part. You can verify this because z over r naught is cosine theta. We have these two complex functions. The linear combinations of these two are proportional to xz and yz. They correspond to the dxz orbital and dyz orbital in the hydrogen atom. Now, m sub L can be plus minus 2. So we have e to the power of plus minus 2I phi. The linear combinations of these two different solutions can make xy over r naught squared and x squared minus y squared over r naught squared. They correspond to the dxy orbital and dx squared minus y squared orbital in the hydrogen atom. The dxy orbital is proportional to xy. The dx squared minus y squared orbital is proportional to x squared minus y squared. I'm just showing you some mathematical derivation here. Xz and yz can be expressed as a linear combination of these two complex functions. So we can add up these two complex functions. We get sine theta, cosine theta, and then 2 cosine phi, and it corresponds to just xz orbital. It's proportional to x and z. We can take the difference between these two, and we get sine theta, cosine theta, and then 2I sine phi. And hopefully you remember cosine theta is proportional to z. Sine theta, sine phi is proportional to y. So this linear combination is proportional to yz. And these two are simply just the xz, dxz atomic orbital and dyz atomic orbital. Similarly, we can also express xy and x squared minus y squared as a linear combination of these two. I'll let you do the derivations yourself. Or we can just look at this page. We can prove xy is and x squared minus y squared can be expressed as linear combinations of these two complex functions. So we can sum up these two complex functions right here, and then we have 2 sine theta squared times cosine 2 phi. Cosine 2 phi is cosine phi squared minus sine phi squared. So we have these two terms. Sine theta times cosine phi is x over r naught. Sine theta times sine phi is y over r naught. So you can see the result is proportional to x squared minus y squared. And this is just the dx squared minus y squared atomic orbital. Now if we take the difference between these two complex functions, we'll get 2i times sine theta squared times sine 2 phi. Sine 2 phi is 2 sine phi cosine phi. Now sine theta times sine phi, that's y. Sine theta times cosine y, that's x. Therefore this linear combination is proportional to xy. And this corresponds to the dxy orbital in the hydrogen atom. So again, in summary, dxy, dx squared minus y squared are linear combinations of these two complex functions. When L is 2, m sub L is plus minus 2. dxz, dyz are linear combinations of these two complex functions. L is 2, m sub L can be plus minus 1. Finally, dz squared is simply y to 0. L is 2, m sub L is 0. This is just to remind you the conversion between x and r theta phi, between y and r theta phi, between z and r theta. Z does not depend on phi, and phi does not depend on theta. And this is the picture over here. Theta corresponds to the latitude, phi corresponds to the longitude. In quantum chemistry, the range for theta is between 0 and pi. For phi, the range is from 0 to 2 pi. Well, now let's look at the shapes of those SPD F-type linear combinations of this y function. We have the subscript L and superscript m sub L. L is the angular momentum quantum number. M sub L give you the z component of the angular momentum. So this is when L is 0. These three are when L is 1, and then m sub L can be 0 and plus minus 1. Over here, L is 2. M sub L can be 0. That's the middle one. This is the middle one. And to the left, to the right, you have dxz and dyz. And this one and this one, well, we have dxy and dx squared minus y squared. So this depiction of dxy and dx squared minus y squared is a little bit problematic, because these two orbitals should not look the same. So one should be about 45 degrees from the other. So you need to rotate this about the z-axis by 45 degrees. When you have dxy, the lobes are on the axis and y-axis, x-axis and y-axis. All right. But when you have dx squared minus y squared, well, the lobes are actually on the diagonal lines. We have F-type shapes as well. When you have F-type functions, L is 3. So m sub L can be from -3 to 3. That's why we have 7 F atomic orbitals. The middle one, we have m sub L equals 0, and correspondingly we have m sub L equals minus plus 1, minus plus 2, minus plus 3. The degeneracy is simply 2L plus 1. When L is 0, the degeneracy is 1. When L is 1, the degeneracy is 3. When L is 2, the degeneracy is 5. When L is 3, the degeneracy is 7. That's why in general chemistry we learn that, you know, you have like one s orbital in a given shell, 3p orbitals 5d orbitals and 7 f orbitals.